All right, let's go ahead and get started. Thank you everyone for joining us today for an overview, a demo of the Zen and art of AI ML on Kubernetes. My name is Saad Malik, and I'm the CTO and co-founder here at SpectraCloud. I'll be the host for the webinar. Joining me is Deepak Sharma, who's the software engineer at SpectraCloud, working on some really interesting technologies with Cluster API and AI ML and GPU. And before we begin, I do want to mention, feel free to post your questions during the presentation and demo using the Zoom webinars question section. We'll try to answer these questions as part of the presentation, and time permitting, we'll also host a live question answer section towards the end. Next slide. So for the agenda, we'll look at why AI and machine learning and deep learning with Kubernetes. We'll look at some of the high-level artificial intelligence and machine learning phases and tools, and then we'll do a little bit of a deep dive in terms of how do you effectively use GPUs and the device plugins in Kubernetes, followed by a demo. After demo, we'll also kind of go into why SpectraCloud makes AI ML easier and how we take all these different tools and combine them to make it easy for end users to be able to operate production-grade Kubernetes clusters. So for the first section, the machine learning on Kubernetes. Next slide, please. We all know that Kubernetes has emerged as a de facto runtime platform to run and manage containerized basic workloads. For containerized workloads, Kubernetes provides significant capabilities with little or no effort involved. Everything from like application deployment to scaling, updates, resiliency, all of these capabilities are provided natively. So this application portability is also enabled with Kubernetes, whether you want to run these workloads on-premise, in the cloud, or in the edge. So what makes machine learning a good use case to run Kubernetes? Well, for one, there are hundreds of different AI and ML frameworks and tools that data scientists use, and there's many more being developed every day. Each of these tools have a very rich lifecycle when it comes to installation, when it comes to security, upgrade, and other day-to operations. With standardized tools such as Helm charts and Kustomize and others, it's really relatively easy now to install and manage all these different tools. Tomorrow, if you don't want to use a specific machine learning framework model, you can just Helm chart a new one and remove the other one. It makes it very easy to swap in and out different pieces of the platform. On a different topic, both machine learning and Kubernetes are very complex platforms with many different moving parts. Over time, organizations develop specialized teams who manage the infrastructure and a different set of teams who are managing the actual platforms and the applications that sit on top of it. With Kubernetes, you really can have a specialized team and operations teams whose sole responsibility is to maintain the infrastructure and making sure to provide the best experience to the end users of the platforms, which could be the AI ML teams or other general purpose compute teams. And lastly, for the effective resource utilization, Kubernetes is at its core an application workload scheduler with algorithms to optimally place different workloads depending on the resource requirements, whether it's CPUs, memory, storage, networking, or others. So with Kubernetes itself, AI ML can be effectively place as many of these resource units as you want into each of the clusters. And AI ML by itself, by its nature, is very bursty depending on the activity you're using. For instance, during the data import and preparation phases, the system needs heavy storage and potential network utilization as it's pulling in all the data. But during training, the machine learning model requires heavy bursts of CPU usage, or if you're using hardware accelerators like GPUs or TPUs, can use this as well. With Kubernetes, it makes scheduling and everything very easy to use. So what is AI? And next slide, please, Deepak. So artificial intelligence is all around us, right? It's everything from your Google Assistant to the computer that's playing a chess program to your automated mortgage approval. AI enables machines to learn from experience and observation, and they continuously adjust their responses based on the inputs that they're receiving. And in the broadest sense, you can think of as AI as any algorithm or program which does something intelligent. So there is a subset of AI called machine learning, where the systems use a large data set to perform automatic approvals, to learn from it, and object recognition and speech recognition and others. And this machine learning teams are essentially, these projects are used for recognition of patterns. And again, they teach themselves how to become better at making predictions. There is also even a deeper layer in machine learning called deep learning, which has the ability to not only make the predictions, but to automatically identify the features and characteristics which play an important role in making these predictions. And this is all done without much human input of any sort. For the purposes of this talk, we'll focus mainly on the machine learning, since like in the diagram, deep learning really is included as part of this phase. Now, machine learning itself has two different phases. There is the experimental phase, which is where the model is really developed and built, and the production phase where the model is deployed into production. Next slide, please. So like I mentioned, right, the experimentation phase is where you really take and you develop the model that is going to be used for your predictions. During the experimented phase, there are multiple different stages the phase goes through. The first phase is the data preparation phase. In the data preparation phase, the actual machine learning, the machine's data scientists will take all of the actual data that they have and clean it up. During the cleanup itself, the operations which are done are things like removing all duplicate data, fields which may not have all the proper data added. They are either imputed, meaning the averages are added from different columns, or those records are completely removed. It's predicted that around 40 to 50% of a machine learning scientist's time is spent in this first phase of data preparations. For the next different stages in experimentation, the model training and experimentation, it has a couple of different variations. The first aspect is building a model. And the model itself is essentially saying, how do I take the incoming data itself, how do I map it into making accurate predictions? And there's multiple different choices the machine learning scientists have. You know, some are built that are optimized for GPUs, others are optimized for different programming languages. And so you have a variety of different choices. But in the end, you know, it's up to the data scientists to choose from the different tools that they have available what makes most sense for the infrastructure that they're running on, as well as for the problem that they're trying to solve. During model training, large sets of that cleaned input data is fed into the model, and through a process called fitting, where each pass of where the data is coming in, the model gets better at predicting what the results need to be. This is a highly iterative process where multiple iterations of this actual data comes into the model itself, and multiple iterations where you're tuning your parameters to ensure that your model is learning and able to make accurate predictions. Once you have a trained model, the next phase of machine learning is the production phase. Production phase is where you take your trained model and you deploy it for inferencing. Inferencing is just a fancy word for saying, let's go ahead and provide APIs that clients can use to be able to make predictions on unseen data. And with production, you generally are also monitoring your behavior of your actual model. And over time, you're also correcting if there are new source of input data coming in, you need to retrain your model. So that whole performance monitoring is also done. On the right-hand side in the diagram, you can see a bunch of different tools that scientists might want to use. And like I mentioned, there are hundreds of different variations and different tools for each of the different stages available. Next slide, please. So if you take a look at some of the more higher level tools that are actually used as part of the experimentation phase as well as the production phase, the first one that comes to mind is the Jupyter Notebook. Jupyter Notebook is a Python-based interactive web application which provides a very easy mechanisms for people to be able to share code snippets and run analysis and tooling, all from a single pane of glass, all from a single UI tool. Most people who use Python for machine learning are very familiar with Jupyter Notebooks, and this is very easily used for most projects that are in machine learning. Kubeflow is a holistic platform in that it provides majority of the tools we saw in the previous slide, as well as Jupyter Notebook, Everything from Jupyter Notebook, Katib, TensorBoard, metadata, all these different tools are bundled as part of Kubeflow to make it easy for machine learning scientists to be able to leverage all these technologies without having to install these things one at a time. And on top of that, any dependencies that may be required for Kubernetes, things like being able to install your cert managers or Istios or ingress controllers, all of these dependencies are automatically handled and installed via Kubeflow. Now, Kubeflow itself does have it has multi-tenancy capabilities. So if you have multiple teams that are leveraging AI and ML, right, you can kind of segregate them based on different users. The only challenge though is that Kubeflow itself because it's a massive platform, has its own very difficult maintenance release lifecycle, and upgrading it from version to version is difficult. And part of the demo will show you how Spectral Cloud can help, not only with the installation of Kubeflow, but also keeping it up to date. So with that, let's switch gears a little bit and maybe have Deepak tell us a little bit more about himself, and also how GPUs can be leveraged for AI and ML. Deepak, over to you.
Thanks, Saad. Hi, everyone. I'm Deepak, and I have been working with Spectral Cloud for past 1 year on the orchestration engine, during which we have designed it using Cluster API and ported it on made it support almost all the major clouds. And it has been a wonderful journey so far. And during this time, we have been presented a challenge to enable Spectral Cloud to enable the GPU supports. So I will be guiding you through the challenges that we have faced to bring the GPU support on Kubernetes clusters, and later on we will be going through a demo. So in this presentation, I'll be taking you through the components and setups required to run GPU-enabled workload on Kubernetes, followed by setting up a GPU-enabled cluster on VMware vSphere with Spectral Cloud and a Jupyter Notebook sample and the cats and dog classification on the same cluster. Before we proceed, let's take a look at the setup that a pod requires to interact and work with NVIDIA GPU. We need device driver and shared libraries installed on the host machine, and these kernel modules depend on the host kernel version. Now imagine we want to pack an application that need to interact with NVIDIA GPU or maybe use CUDA libraries. We can't directly pack these dependencies in the container, as the container would be tightly coupled with the shared libraries or the kernel modules it has. We can't port this container on a different host that doesn't have the same kernel version or shared user libraries. So we need a way to make our workload portable. In terms of Kubernetes, we need a way to share the NVIDIA user libraries and device drivers installed on the host to be made available to the container. For this purpose, Kubernetes has provided a solution using extended resources and device plugin. Let's take a look at them. Kubernetes can manage workload requests using resource limit and request. But what if pod needs resources apart from CPU and memory? For managing and scheduling such workloads, Kubernetes provides extended resources. Kubernetes is just aware of the number of such resources. These resources remain totally opaque to it. Kubernetes scheduler listens to such resource requests and assigns the workload to a node that has a capacity to satisfy the workload requirement. Now, this type of scheduling brings certain limitations. As these resources are opaque to Kubernetes, it doesn't allow the overcommitment of resources, and resource can only be consumed in the integer values. Unlike memory, we can't have fractional values for an extended resources. So a pod can request a whole number such as 1 or 2 of GPU, but it can't request 1.5 or 0.5 of it. As Kubernetes doesn't directly manage these resources, pod can't share them. And an extended resource is fully dedicated to a pod that it got assigned to. In our case, device plugin advertises these resources, NVIDIA.com GPU or the GPU devices to kubelet, and it gets made available to the node capacity. Here in the diagram, we can see our third node has a capacity for 2 GPUs. Let's see what happens when a pod arrives requesting extended resource NVIDIA GPU Scheduler goes ahead and finds a node, the third node in our case, and the workload is assigned to the third node. Scheduler here doesn't know about what exactly the device is or what it does. The one thing scheduler knows is that the node in the cluster has the resource available. How this device is managed or how this device is made available or even how the device operates, it's totally opaque to scheduler. The necessary setup for a device to work is done by device plugin. Before we move to device plugin, we have another component in our case for NVIDIA GPU, which is device driver installer, which has a responsibility to install NVIDIA device driver and other utilities on the host so that device plugin can later use them for pod creation. Let's take a look at device driver installer. Device driver installer is responsible for checking and installing the latest version of NVIDIA device drivers and utilities on the host machine. Device driver runs in a reconcile loop where it checks for the host whether it has NVIDIA tools installed on it or they are up to date for the given host kernel version. If the tools are missing or need an upgrade, driver installer will either install these tools or will perform upgrades if necessary. In our case, on the host, driver installer under a set directory, home Kubernetes wing NVIDIA will install the NVIDIA tools and libraries. Let's take a look at what this directory looked like after one successful reconcile from the driver installer. On the host machine, we can see that it has installed NVIDIA utilities such as NVIDIA SMI, NVIDIA settings, NVIDIA modprobe, and under lib46, we can see it has installed all the shared object libraries such as libcuda, libopenGPL. Later, device plugin will use the contents of this directory present on the host to be mounted inside the container. So that container can have access to these shared libraries. Now let's take a look at device plugin. So you have a device and you want this device to work with Kubernetes. You use extended resources to manage it in Kubernetes, but that's not the end. Kubernetes has defined a device plugin interface that allows device plugin to manage these devices and have an interaction with kubelet so that the kubelet on the host or on the node is aware of the devices and the capacity it has available. Device plugin spec has two services. One is registration and a stream for devices, and another one is for the allocation where it negotiates with the device, where the kubelet can go ahead and negotiate for the device plugin for the resource it is going to create. Let's take a look at them one by one. The first step for a device plugin is device plugin registration. So when a device plugin starts to run on a host machine, the first thing it comes up and does is that it registers itself for a given extended resource with the kubelet, along with the information what is the device plugin version that it is supporting, what Unix socket it will be listening to for the further calls, and some other information if it wants to share with the kubelet, it can share. Now, after the registration for an extended resource, kubelet knows that the given device plugin is responsible for the given extended resource. In our case, this is nvidia.com/GPU. Once the registration is done, the device plugin starts a stream of devices it watches. This stream returns a list of devices that this device plugin is able to find and are healthy. This list of devices is used by scheduler to allocate the request for extended resources. Device plugin has the responsibility for probing and keep reporting the devices and their health status back to kubelet. Now that kubelet is aware of the device plugin responsible for our extended resource and it knows how to reach back to it for the allocate call whenever a pod with a request for given extended resource arrives. Now let's take a look at what device plugin is seeing on the host machine. After the registration and probing the NVIDIA GPU cards on our case, on the host machine, device plugin has the information for mount path, which it is going to use from the host where we have done the installations. And this mount point will be negotiated with kubelet so that the container, it can be mounted inside the container at a specific location, and container can access the content inside it. Now let's see what happens when a pod has arrived and a device, and kubelet has a allocate call with device plugin. When a request comes to device plugin via kubelet for a given device, in allocate call, device plugin can inform the kubelet with all the initialization requests that is required. Device plugin can pass specific environment variables specific to the device setup or other information that need to be passed as environment variable. Device plugin can pass multiple mount points from host to be mounted inside a container at a specific location. In our case, this is the directory where our driver installer has installed all the NVIDIA binaries and libraries. This way we can share our NVIDIA utilities and install shared object files to the container. Device plugin also publishes all the requests, all the response which is related to a device, where the device is located on the host, where it is going to be mounted on the container, and the necessary permission related to it. Additional information such as annotations can also be passed in the response. Then kubelet, once gets this response, can use this information to populate the pod. Now let's take a look at an end-to-end scenario. What happens when a request for a given extended resource arrives? A user creates a workload requesting a given extended resource, that is NVIDIA GPU in our case. Then scheduler picks up this request. Scheduler then decides that the node which has the capacity for this extended resource, this request gets assigned to one node. The kubelet on the node picks up this request and then negotiates with the device plugin. Device plugin in the response sends all the information which is required for the device, for the pod or the container initialization. Now let's see what the pod sees when it has come up. When the requested pod comes up, it has GPU card available to it, and under the path user local NVIDIA, it has files mounted from the host. Now it has access to all the NVIDIA tools and all the driver installed, and has all the libraries which it requires to interact with the GPU card. So the pod can now start behaving as if it has all the things which it requires to access and interact with the NVIDIA GPU card, and can start with the task. Now, next for demo, please wait while I set up for the demo. Please allow me a minute.
And people, if you guys have questions about either AI ML or the platform or any of this aspect, please feel free to ask them in the question answer section.
Hi everyone. Let me take you through the demonstration for provisioning a GPU-enabled cluster using SpectroCloud. SpectroCloud allows users to define a cluster in a declarative template that we call cluster profiles. These cluster profiles consist of several layers that a user can customize depending upon its need. Let's take a look at one such cluster profile. This cluster profile I have created for the VMware GPU. Inside a cluster template, a user can select the OS family and the version it wants to configure the Kubernetes cluster with. It can select the Kubernetes release version, can configure the CNI and CSI layer. And on top of that, a user can configure any system app that it wants to. Kubeflow in our case, or user has an option available for different kind of applications. And through the values like Helm chart values, we provide the option to totally customize the application according to the user needs. So user can fill or customize the application to suit its need. So this is the cluster profile. Let's start configuring a cluster using this. We will be configuring a VMware cluster. we will use the cluster profile which we have just seen. We can have a quick look at it, that it has all the components, right components that we want. We can edit the parameters and provide specific values if required for this particular cluster. Here, we can select the VMware specific details such as the data center or the folder that we want to create our cluster into. And here we have nodes configuration. This allows us to customize the master pool and worker pools and even add more nodes or the pools to our Kubernetes cluster. We can specify the number of nodes in a pool. We can specify the CPU or the memory and the disk capacity of the underlying virtual machines. Let me do a quick setup here. Similarly, we'll copy the same configuration from master pool. On master pool, we will select the GPUs which are available in our data center, and we will provide the count which is required for this. Now this cluster configuration looks good. We will have one master and one worker pool, one by one cluster created. Everything looks good. We have Ubuntu OS, Kubernetes, and the Kubeflow system app installed. Now let's deploy the cluster. This cluster creation will take around 10 to 15 minutes. I have a cluster that is already provisioned. Let me take you to that. So this is a Kubeflow installation on the cluster, on a similar cluster where we have the Kubeflow installed. So I will be taking you through an example of Jupyter Notebook. So we have one server that is already running. A user can come and provision any Jupyter Notebook server that it wants, and user has option for specifying the custom images they want and can specify the CPU and RAM for it. Now, this is the Jupyter Notebook that has been running. And let me take you through one of the notebook that we have. So this is a sample cats and dog classification example where we have installed some of the Python libraries. Then we use TensorFlow for the training. We import the cats and dogs data. We prepare our data. And after that, we prepare the images, and this is the model that we will be going to use. The first layer in this model has two-dimensional. This is basically a CNN, and it has two-dimensional. First layer has two-dimensional CNN, and then there are 32 output filters. So this is the summary for the given model. Here we start our training. Here is where exactly we start to fit our data, and I have already run this for a training in 5 epochs. So you can see the loss has reduced and the accuracy has kept improving. Now these are the test predictions that we have. We can see that the model has fitted quite well apart from the first exception. And let's see the model performance now. So this is the plot. This is the confusion matrix. You can see that these are the false positive it has got, and how efficiently the model has performed. Okay, so that's it from the demo perspective. Back to you, Saad.
Well, thank you, Deepak. Great job on the GPU presentation and the demo for Kubeflow. So as you can see, Kubeflow provides a rich AI and ML platform with integrations for Jupyter Notebooks. There's many other aspects that Kubeflow also provides, which obviously we didn't cover today. And using Spectral Cloud, you can use this profile-based management to effectively provision and maintain all your Kubernetes clusters whether they're running Kubeflow or other AI ML platforms running inside of it. And also the aspect of having a finite set of resources like your CPUs or memory, being able to manage those and share them out across clusters, including GPUs and TPUs, where you can effectively say, I want to assign these Tesla K80 GPUs into my cluster C1 and use the other set of GPUs for another cluster. So that, and maybe you can go back to the slides, Deepak, but that's pretty much it that we had from the presentation and demo. Are there any questions that anyone has? Feel free to raise your hand or just ask the questions in the Q&A box, please. All right, guys. Well, thank you so much for attending our webinar itself. I hope you enjoyed this. We will be publishing the slides and the recording later today. Thank you so much, guys. Thanks, Deepak.
Thank you. Thanks, everyone.